Everyone are exposed to be injured when doing any physical activity, especially of course in athletes. According to statistics taken by Stanford Children's Health, legs are the part of the body with most cases of injuries in all sports. The use of splints has become very common either because the injury, the process of rehabilitation, or even to be more secure at the time to compete. Having said the above, we decided to develop a leg splint that can be used to stabilize injuries by decreasing movement and providing support, thus preventing further damage. It also alleviates extremely pain, edema, and further soft tissue injury and promotes wound and bone healing. Our splints can be used for immobilization of an extremity before surgery or as a temporizing measure before orthopedic consultation.
Here we have our final product. It's a leg splint, a modern leg splint. The advantages between this one and the older ones are that these one are more comfortable, have better advantages because the freedom that gives to the user, and a lot of other things. To create a mold based on this splint, we have some challenges that we solved by, first of all, creating in two parts. We separate from here in order to create two parts of models, and at the end we need to get it joined together to get this final result. Well, the first step was to create a solid mold. So at the beginning we have to make this a little bit more bigger. So we do this, then we, as we already said, cut it in half and create it complete solid. So in this way we have the first step done. We have here the right part of the splint. So it's gonna be the same with the left part. Now here we can observe that we have our molds done. Well, now I'm gonna explain you how does this works. The first one and the most important are these, because this one is where we are gonna get our material birth. Another important thing that we have to to see is that they have these air escapes in order to not get a lot of pressure under the mold, and in this way the air is going to escape from the mold and when it's already ensembled, and also maybe a little bit of material, but in this way we're gonna be sure that the material gets in all the mold. We can observe that when we create the match between these two parts of one mold, I will show you how we think about everything. Okay, as we can see, here are the air escapes where all the air and the pressure is gonna get out from the mold. I have another one, and here is where we're gonna birth our material to the mold. Now I'm gonna explain you how does this mold is thinking. As we already mentioned, here is where we are gonna put all of our material, and the material is gonna get in the mold, and we can observe here that we have an air space right now because is where all the material is gonna be. We can observe here all of this part is where the it has air right now. We can see it from the top view, and when we put it like this and put all the material is gonna get in this air space right now. It's important that to see that in this place at the top we didn't have anything because we just wanted to be laminar or mold, as we already showed you the final product. And for example, when we finish to put all of our material in this mold, we're gonna have just the half of the splint. So it's the same process with the other half, and then we're gonna join together both parts and in order to get a final product that we already show you. But the important things here is that we have this mold, the airscapes, and the space between them. It's around 3 millimeters between one mold and the other, this airspace. Then it's gonna fill with material at the end.
Well, the next step after generating the mold in SolidWorks is to export them in Fusion 316, that is this program, and generate the trajectories like this to subsequently generate the G codes in this part. In this case, we have two different molds. This one, uh, this is the mold number one, the top part. This is the top part, and this is the bottom part for the mold number one. It's working. And this is the bottom part, and for the mold number two, this is the top part and the bottom part. And as you can see, these two parts are like the same geometry, but in the opposite side. As you can see, it's like the same, and uh, the same for these two. That is why we use like the same trajectories and the same tools. First, uh, well, after this program show us different types of 2D trajectories and 3D trajectories in this part and in this part. Uh, for our molds, we use the 3D trajectories. This is because um, we have curved surfaces, like in this part, we have curved surfaces, and this orifice. Um, and the most complicated when choosing the trajectories was that I was not very familiar with the program, and the mold was curved surface, and it has holes like this, and this made it our mold more challenging, I think. And well, for the first two pieces, as you can see, we use the same or similar trajectories and with the same tools too. Um, in I will show you the with this with this piece. The first five trajectories are this one that I'm showing in these ones. 1, 2, 3, 4, 5, and these were to make the air outlet, and I use a 1 millimeter diameter tool for this because the air outlet was so small. And then I use this path to define the underside of the spin well. I use the ramp because the curved surface, and this for this I use a 3 millimeters diameter tool, and then I use this trajectory, this to define this part, because in with this trajectory this part was not very well defined, and with this part I can define this very well. As you can see, it made the holes. And the last trajectory that I used um, was to remove the excess from the top of these ovals, because there was a lot of material here in some parts, and so I use this trajectory with a 5 millimeter tool. And in this part, as you can see, the same trajectory was used, um, because it's like the same form, just the opposite side. As you can see, I can show you this part. And then for the bottom mold or pieces, uh, like the same, I use the same trajectories for this, because also is the same, like uh, the same part, but in the opposite side. And first of all, I use this trajectory, all the outside part, and the excess will remove with this trajectory. As you can see, all this part was removed, because the the piece is all of this. And to remove this excess, I use this trajectory with a 10 millimeter diameter tool, and later I use this um, to define better the contour of the piece. This trajectory was used with a 3 millimeter tool. This is a smaller tool, because this part is need to be better defined. And finally, I use this trajectory with a smaller tool, with a 1 millimeter tool, uh, for the ovals in the middle of the part. Uh, we can see that with this trajectory we can cut all these parts. And also for this mold, where the same trajectories, as you can see, the contour and the ovals. And uh, another important thing here in Fusion 316 is that for all the molds we can like simulate, after to generate the G code, we can simulate here in this option. We just wait for this, and We can simulate all the trajectories that we propose here, and here we can see also all the all the trajectory mm, that is made. And also, for example, if I go faster, this is the trajectory. And also we can see the change of the tool. For example, in this position is it will change the tool. You can see the change, and it is the contour, and then we see the holes here with this. And then finally you can close this. To generate the G code, we select in here this G code, and we can select to use in CNC Base the Fanuc with this. The code works well, and then post it, and then we can put a name, for example, I don't know what you want, and then we'll generate a code. This code you can copy and then paste in CNC Base to see all the simulation.
After we export our CNC code to CNC Base program, in where we can see how a real machine, a milling machine, can produce our product, we're gonna see if our simulation in Fusion was executed correctly. And here we're gonna see step by step, tool by tool, how does the work is done. Every single tool must be the same as large and the diameter as the ones that you have in Fusion. Be careful because in CNC Base you need to change the tool diameter by yourself. This is not automatic. Most of the times, as you can see in the code, they told you as comments how does these tools are, and then you just need to open the tools and edit one by one in order to get exactly the same as the ones that you have in Fusion. You can see here that the simulation is done uh, step by step, and if you change the view, the simulation is gonna restart but in a very speed way.